Hi, this is my submission for the Altair Global Student Contest. My name is Adi and I am from the Indian Institute of Technology, Hyderabad. For this contest, I've chosen a robot built in the first robotics competition by the team AlphaBots as a part of the World Reefscape Championship. So let's go to the model. So this is the model made by the AlphaBots in the first robotics competition 2025. The purpose of this bot is to play a set of games including picking up and placing PVC pipes and rubber balls. So in this video we are going to be optimizing three major parts. The first part is the shaft support bracket, which connects the arm to the carriage. The arm is meant to rotate for accurate grabbing and shooting. Next, we'll be optimizing the feeder shooter plate, which is responsible for grabbing and shooting the balls in the PVC pipes. It has flywheels attached to it. And lastly, we'll be optimizing the rear intake motor mount, which connects the flywheels to the carriage, and that is responsible for the intake. So let's start with the shaft support bracket. I've partitioned the bracket so that the holes are left untouched, and I've performed a topology optimization for maximum stiffness. So this is the desired result which I want. Next, I've converted this to a polynobe shape as such. So now I've converted the polynobes part into a solid step file. This weighs about 115 grams. Now let's go towards motion analysis. So this is the motion analysis of the optimized part. We see that it has a maximum displacement of 0.37 millimeters. However, it has a minimum factor of safety of 0.8, which is not very desirable, as we generally prefer a factor of safety of above 1 or 1.5. So Altair Inspire allows you to observe parts which tend to fail. And now that I've obtained those parts, I'm going to manually edit them so that our support structure is a bit more stable. So I've manually reconstructed the support bracket. So now it weighs 132 grams. Over here I've thickened the parts which failed last time for improvised stability. Therefore, this is the final motion analysis of the optimized part. We see that it has a maximum displacement of 0.02 millimeters, and it has a minimum factor of safety of 1.7. So we have decently optimized this part, and at the same time we've reduced its weight from 179 grams to 132 grams, a mass reduction of 26%. Now moving on to the next part, which is the rear intake motor mount, which weighs at 42 grams. Let's perform a topology optimization for maximum stiffness on this part. In this topology optimization of the rear intake mount, I've partitioned the part so that the part bolted to the carriage and the ring around the bushing remains unchanged. After setting a suitable point at the material slider, I'm going to convert this into a polynobes part. After having done that, let's go towards motion analysis. In the motion analysis results of the optimized part, we see that the maximum displacement of the part is in the order of 10 to the power negative 3 millimeters. It has a minimum factor of safety of 112 and a percentage of yield of less than 1%. This new optimized part weighs at 20 grams as opposed to the original 42 grams, and it has a net reduction in mass of 52%. Finally, I've run a static analysis on the feeder shooter plate, and then I've performed a topology optimization on the plate. This part originally weighed at 423 grams. Then I've converted this into a polynerves part. However, we see that this isn't very symmetrical, so let's try to obtain symmetry in this. After converting the polynerves part into a solid step file, I've mirrored the right part onto the left so that this feeder shooter plate is a bit more symmetrical. Lastly, I've run a static analysis on the feeder shooter plate. The forces over here represent the belt reactions on the bearings, and this has a maximum displacement in the orders of 10 to the power negative 2 millimeters, a minimum factor of safety of 180, and a percentage of yield less than 1%. This part now weighs 352 grams from the original 423 grams, and this has a total mass reduction of 17%.